Welcome to another webinar session by Academics, a training division of Aegis Computers India Private Limited. Today's topic is Introduction to the Design Considerations for Buckling Calculations of Steel Structures. Myself, Vishnu Shivan. I'm an MTech design engineer from Aegis Projects. I have more than 6 years of experience in design and new product development. Most engineers and designers are aware of failure due to tension or bending loads. However, when the structures are subjected to compressive loads, another mode of failure results due to the loss of instability. Buckling as a mode of failure cannot be determined by a simple stress analysis. Here, we shall outline how buckling is calculated, when it should be considered as a failure mode, and a few techniques to carry out a buckling analysis. Before starting the session, let's go through some loading scenarios which are subjected to a long column. Here we have a long column that is subjected to a tensile load. Due to the application of tensile load, at a certain point, the long column shall fail by elongation because the stress generated at the necking region exceeds the tensile strength value. A compressive load has been applied to the same long column. This load compresses the column and it fails by crushing at the center because the applied load exceeds the compressive strength. However, there is another situation in which the same long column collapses under a compressive stress. During the compressive action, at a certain point, the long column shall fail by deforming the shape. This does not result in yielding or failure. But this is also considered as a failure because right now it is not capable of achieving its purpose. This failure is called as buckling. Let's go through some common and uncommon examples of buckling. Some of the common steel structures used in power transmission, scaffoldings, crane support structures are mostly subjected to buckling failure. When rail tracks are subjected to sunlight, it gets heated. This creates unwanted compressive force in the rails, which results in buckling. Due to this, rails move laterally, often pulling the underlying ties along. Similarly, offshore pipelines may also experience similar scenarios when it carries hot fluid to transfer. Another example is a conventional bicycle wheel consisting of a thin rim kept under high compressive stress by the inward pull of a large number of spokes. Today, we shall go through these details of buckling. Importance of buckling calculation, mechanics behind buckling, governing factors for buckling calculations, tools for determining buckling loads, analytical and FEA calculations. So, what is buckling? Buckling is a loss of stability that happens when the applied compressive load reaches a certain critical value. This usually results in the deformation or the distortion of structure shape. That means the straight member will buckle immediately by producing a large displacement. This doesn't always result in yielding or failure of the material. But buckling is considered as a failure because the structure no longer supports the load the way it was designed to. Okay, how do we consider buckling in our engineering design and analysis? For that, we need to travel back to 17th century. The mathematics of buckling was first explored by Leonhard Euler in 1744. In his book Calculus of Variations, he explained an equation for the axial load that will cause a column to buckle. It is one of the oldest engineering design equations that still in regular use. That is called Euler's equation. We can go through the terms in Euler's formula. PCR is the critical load, E is the Young's modulus, I is the area moment of inertia, L is the length of column. That means it doesn't depend on material strength. Okay, let's go through each term. I is the area moment of inertia. We can consider a rectangular section with a width b along x-axis and breadth h along y-axis. The area moment of inertia about x-axis is given by bh by dot. Similarly, the area moment of inertia about y-axis is b cube h by dot. From the equation itself, it is clear that the value of Ixx is smaller than Iyy. As per the design criteria, we must choose the smallest I value for the calculation. The next term is L. It is the length of the column. Based on the connections, we have mainly four end conditions. The first one is fixed ends. A long column with a length of L fixed at both ends. The second one is pinned and fixed ends. The same long column with one end pinned and other end fixed. The third one is pinned ends. Here, both ends of column are pinned. The fourth one is fixed and free ends. Here, one end is fixed and another end is free. In the actual case, the length L is used by another term called effective length LE. It is the length of a component which is effectively restrained. For each condition, values are different. For fixed end, it is 0.5 times actual length of the column. For pinned and fixed ends, it is zero point 0.7 times of L. For pinned ends, effective length is equal to the length of actual column. For fixed and free ends, it is double the length of actual column. It can also be represented as length factor K. That is, for fixed ends, length factor is 0.5. For pinned and fixed ends, length factor is 0.7. For pinned ends, length factor is 1. For fixed and free ends, length factor is 2. Okay, let's find out some buckling loads. Here, we have considered a circular beam of diameter 100 mm, which has a Young's modulus value of 210 GPa. The length of the column is 10 meter or 10,000 mm. We know the area moment of inertia relation for a circular beam. That is, I is equal to pi d raised to 4 by 64. Also know that area moment of inertia for a circular beam is same for both axes. Substituting the known terms gives the area moment of inertia value. That is 4908738 millimeter raised to 4. By using the Euler's relation and substituting the values of Young's modulus, area moment of inertia and effective length, we shall get the buckling load for all four conditions. Here we have the end conditions, the effective length and the buckling loads. Let's take a look for the obtained values of buckling load in each end conditions. Another important term is critical stress. To obtain this, we need to divide the critical load with the area. That is, it is the ratio of the critical load with respect to the area gives the critical stress. Sigma CR is called the critical stress. Here we can see that the terms I by A. We know that the square root value of I by A is called radius of gyration. So we can replace the term I by A to R square. By rearranging it, we have this equation. The term Le by R is called slenderness ratio. Let's find out the effect of slenderness ratio in Euler's equation. When we plot the Euler's critical stress with the slenderness ratio gives this type of relation. We know that buckling occurs before the yield stress value. The vertical line is called limiting slenderness ratio, which depends on material's Young's modulus and yield strength. If a column's slenderness ratio is below this limit, it falls under inelastic buckling limit. This is only a theoretical behavior of the column, but in experimental results, we have this kind of behavior. Based on the slenderness ratio, we can define whether column is a short column or intermediate column or a long column. Let's consider this plot for a structural steel column. For columns that are having slenderness ratio less than that of 40 comes under short columns. The slenderness ratio between 40 and 150 is an intermediate length column. The slenderness ratio greater than 150 is long column. Tools for calculating buckling. One important tool is spreadsheet. There are readily available Excel sheets which have predefined structural section details with material data. You need to add relevant inputs to find out the buckling load. A person with good skill in Excel can create a unique sheet based on his requirements. Tables. Tables provided in steel construction manual, especially in AIC steel construction manuals, are also useful for determining different effective lengths that modify the calculation of critical loads. Another option is software-based FA calculation. This can be used to run a buckling study to calculate the critical load. This can be particularly beneficial when the geometry involved is that of a system acting more as a larger system in a composite action, or if it has irregular cutouts that make the stiffness change along the length of the beam. We can move on to the next stage. Let's do some validation of Euler's equation for buckling load calculation. For the validation, we have selected a universal beam of size 127 cross 76, which has a weight of 13 kg per meter. Flange width, beam height, flange thickness are mentioned in the below figure. Young's modulus value is 210 GPa and the length of column is 5 meter or 5000 mm. We know the buckling equation and already know the E value. We need to find out the area moment of inertia and to select a suitable end condition. The I section has been divided into three sections. Width and depth of each sections are numbered from 1 to 3 respectively. B1, B2, B3 are the respective width of each sections, and D1, D2, D3 are the respective depths. H1, H2, H3 are the distance from centroid for sections 1, 2 and 3. Since H2 lies in the same location of the centroid, the value of H2 becomes 0. We know the area moment of inertia relation for a rectangular section. Using that equation, we get the moment of inertia value of Ixx at section 1. Moment of inertia about axis xx1 gives the value of 2061398.56 millimeter raised to 4. Similarly, for section 2 and section 3, we have these values. Summation of these three section values provide the area moment inertia of the universal beam about xx direction. Similarly, in the yy direction, we have to calculate the moment of inertia. Y-axis of all section lies on the same line. Applying the moment of inertia relation for each section, y-axis gives these values. Summation of these three section values in y direction gives the area moment inertia of the selected universal beam about yy direction. Now we have the values of area moment of inertia in xx direction and yy direction. We have already mentioned that the design calculation should be based on the smallest moment of inertia value. Therefore, the value should be used for the buckling calculation is Iyy. Let's check out what are the values of buckling load if the same structural column is used in different end conditions. We have the end conditions and we know the effective length in each condition. Applying Euler's relation, we get the buckling load in each end conditions. We have gone through the analytical method. Let's go through the FEA method.
Hello everyone, my name is Jitu PV, MTech Machine Design. I am working as Design Engineer in EGS Computers India Private Limited. Earlier, we discussed the fundamentals of buckling and studied and discussed the details of Euler's equations with different end conditions. And we are also calculated the crippling load of an I-beam under Euler's equations with different end conditions. In this session, we are going to model the same I-beam in Solidworks software and going to simulate the I-beam for buckling and with the different end conditions and obtain the crippling load from different end conditions, and we are going to correlate the FEA results to the analytical calculations. The I-beam is alloy steel universal beam with standard dimensions of 127 mm depth and 76 mm width. The thickness of the flange is 7.6 mm and web thickness is 4.2 mm. First, we are going to draw the I section in the Solidworks software. Now we have to select a plane, and now we are going to select the center line. First, we are going to draw it in the XY plane. The purpose of drawing the center line is for reference purpose. And we are giving an arbitrary height of length of 150 mm to the center line. And as the first step, we are going to model the bottom flange. So overall depth of the I-beam is 127 mm and the overall width is 76 mm. So I am giving half of the value. So the thickness of the bottom flange is 7.6 mm. Here both the bottom flange and top flange of the I-beam are symmetric. That is, both of the top flange and the bottom flange have similar dimensions. So the overall depth of the I-beam is 127 mm and the depth of the width itself is the depth of the web itself is 111.8 mm. Next, we are going to model the top flange. Now the one part of the I-beam is completed and we are going to mirror these entities. Now we have to select the mirror entities and select all the parameters, all the edges that is going to be mirrored. And next we have to select the axis that we drawn earlier. And now there is a complete I section is formed with 127 mm depth and 76 mm width. Now as the next step, we are going to extrude this. As I mentioned earlier, we drawn this I section in XY plane and we are going to extrude it in the Z direction. In the earlier analytical calculation, we are giving the span dimension, the span as 5000 mm. Here we are going to provide the same length, same value, 5000 mm span. So we drawn the I section in XY plane and extruded in the Z direction. Now the modeling of the I section is completed. So this is the I section with overall depth 127 mm and width 76 mm with a span of 5000 mm. In the next step, we are going to simulate it for buckling with different end conditions and the obtained crippling load, and then we are going to compare the FER results with the analytical calculation results. Now the modeling of the I-beam is completed and now we are going to simulate it for buckling under different Euler's end conditions. The 4 different end conditions are: first one is one end is fixed and the other end is free. Second end condition is both ends are fixed, and the third end condition is both ends are pinned, and the fourth end condition is one end is fixed and the other end is pinned. After this, we are going to tabulate the crippling load obtained from the simulations, and next we are going to correlate the FER results with the analytical calculation results. Now we have to select new study from here, buckling, and we can rename it and as one end is fixed, other end is free. Now the next step is we are going to treat this, we are designing this I-beam as a 3D element, and now we are going to convert or treat it as a beam element. The reason for this is when we are convert into the beam element from 3D element, the beam member can provide accurate bending or buckling behavior during simulation. And next step is we are going to apply the material. So right click here and we can select alloy steel from the material library, because we are already discussed we are using alloy steel standard I-beam. So apply the material, and next step we are going to apply the fixed conditions. So we are in this end conditions, that is we have one end is fixed and the other end is free. So in the fixtures, right click and we have to set one end as fixed. So fixed geometry, we have to select one end, select one joint and fixed geometry, click here. So this end is fixed. Fixed end means all the degrees of freedom are arrested. That is, all the degrees of freedom including the translation and rotation are arrested and no movement is allowed. And as a next step we are going to apply force. So as we mentioned earlier, the I section is modeled in XY plane and is extruded to a column extruded through the Z direction. So we are applying load axially through the Z axis. So here we have to select an end to apply load, and then we have to select a reference plane, and as a next step we are going to apply the load. Here we are applying unit load, and we can change the direction of the applied load. So the unit load is applied axially through the column. I can change the position for better visualization. Now here it is clear, the one end is fixed, other end is free, and the axial load is applied to the one end, that is we are applying unit load. And now the loading is completed. Next we are going to mesh this model. We have to create mesh, and the meshing is completed. And next we are going to run this study. The solver we are using to run this study is FFE plus solver. And now we are going to run the study. And the simulation is completed, and we will get a load factor of 11,537. And the very important thing is, the crippling load is defined as the product of the load factor into the applied load. That is the force we applied, the unit load. That is, crippling load is equal to load factor into applied loads. That is equal to 11,537 into 1, that is equal to 11,537 Newton. So the crippling load obtained here is equal to 11,537 newtons. So once again I am explaining it. The crippling load is the product of the load factor and the force here. So here the load factor is 11,537, and the unit load is, and the load applied here is unit load, that is crippling load is equal to 11,537 into 1 is equal to 11,537 Newton. So in this structure, that is one end is fixed and the other end is free. The simulation is completed and the structure is buckled, and the crippling load, and we found out the crippling load is 11,537 Newton. And if we are give a load above this crippling load of 11,537 Newton, the structure is going to buckle. Now I am going to simulate the second Euler's end conditions, that is both ends are fixed. So here in this beam, the both of the end, the top end and the bottom end of the beam is going to be fixed. And apart from the end conditions, all the other parameters are not going to be changed. So that's why, so our better convenience, we are going to copy this study. So for our convenience, we are going to rename it to the reason at which I am copying this study is the only thing is going to be changed here is the end conditions, and all the other parameters are not going to be changed. So I just copy study and going to delete this end conditions. And now I am providing the new end conditions, the second end conditions, that is both ends are fixed. So here right click fixed geometry and select the bottom end, join one and give fixed geometry. So fixed end means, if one end is fixed means all the degrees of freedom including translation and rotation are arrested there, so, and no movement is allowed. In the analytical section, the end condition of Euler's theorem is detailed explained. Now I am going to apply the fixed end to the applied fixed condition to the other end. So right click here, fixed geometry, and using reference geometry I am going to arrest all degrees of freedom here. I select the joint and also select a reference plane corresponding to this joint, and I am going to arrest all the degrees of freedom here. And once it is completed, then we can directly run the study, because we already given all the, since it is a copy study, apart from the end conditions, all the other parameters are same. So simply we are running this study again, and the simulation is completed. I'm going to another view, and the simulation is completed, and now the one end of the beam is fixed and the other end is also fixed, and the load is applied axially, and we will get the buckling, and the load factor obtained is 1.841 into 10 power 5, and as I mentioned earlier, the buckling load or the crippling load is equal to the product of load factor into applied load. Here the applied load is 1 Newton, that is the load factor obtained is 1.841 into 10 power 5 is multiplied with the applied load. We will get the crippling load. Since we are using unit load, we will get the crippling load that is equal to 1.8418 into 10 power 5. So in the second conditions, the both ends are fixed, and we run the simulation and obtained the structure is gets buckled, and we obtained the crippling load value here. Now we are going to simulate the third end condition in Euler's theorem. The third end condition is both ends are pinned. So we are going to copy study, and we will rename it to both ends pinned. So here from the previous study, all the apart from the end conditions, all the other parameters are not going to be changed. So we are deleting these end conditions here. So the end condition is now changed. It is both ends are pinned. Pinned conditions means pinned end means only 1 degree of freedom is allowed. So the details about the end conditions, the details about the pin conditions is explained earlier in the analytical session. So I am going to apply end conditions here, that is both ends are pinned. So in the fixtures there is an option called immovable. The immovable is similar to the pin conditions. So if you are going to apply pin condition, that is pinned at one end, we can select immovable. So select immovable and select that particular joint, and next we are going to pin the other end also. So we have to select, we can restrict, so we can arrest the degrees of freedom by using reference geometry. We can select the end conditions here, end joint here, sorry, and we will select a reference plane corresponding to it, and we can restrict or arrest all the degrees of other degrees of freedom. And once it is completed, we are going to run the study. Before that, we have to visualize it. So now in the third end conditions, the both ends are pinned and the load is applied axially. Now we are going to run the study. Now the simulation is completed and the buckling is happened in the structure. And here, as I mentioned earlier, the buckling load or the crippling load is the product of the load factor into the load applied. Here we are applying load is unit load, that is the value is 1. So the crippling load here is load factor into applied load, that is equal to 46,128 into 1, that is the crippling load here obtained is equal to 46,128 Newton. So the structure is, so the third end conditions, Euler's end conditions, both ends are pinned, is simulated and the buckling is obtained. The structure is buckled and the crippling load of 46,128 Newton is obtained from the simulations. Now I am going to simulate the fourth end condition in Euler's theorem, that is one end is fixed and the other end is pinned. So here we are going to copy the study, and rename it 1 end is fixed and other end pinned. So here the only thing is going to be changed is the end conditions, and all the other parameters are similar. So we are going to delete the end conditions here. So the end conditions are deleted, and now we are going to apply the new end conditions, that is one end is pinned and the other end is fixed. Now in the fixtures right click fixed geometry, we are going immovable that we explained earlier, that is similar to the pin conditions. So pinned means only 1 degrees of freedom is allowed, and fixed means all the degrees of freedoms are restricted or arrested, and all the Euler's end conditions pinned and fixed are explained in the analytical calculation session detailed. And now select immovable and select the one end, and it is pinned. And now we are moving forward to the other end. Here we can right click and fixed geometry, and we can use reference geometry to arrest all degrees of freedom. So from here we select the joints, and next we are selecting the reference plane corresponding to that joint, and now we are going to arrest the degrees of freedom. And now we are given the end conditions, that is one end is pinned and the other end is fixed, and we are applied the load axially. All the other parameters are kept similar. Now we are run this study, and the simulation is completed and the structure is buckled, and we will get a load factor of 94295. As I mentioned earlier, we can calculate the crippling load. The crippling load is the product of load factor and applied load, that is force. So crippling load is equal to load factor into force, that is equal to 94295 into 1, that is the crippling load obtained from the study is 94295 Newton. So the simulation, the Euler's fourth end conditions, one end is fixed and the other end is pinned, simulation is completed and the structure is buckled, and we calculated the crippling load as the product of load factor into applied load, that is the crippling load is equal to 94,295 Newton.
Now the simulation of I-beam is completed for buckling under different end conditions. Next, we are going to correlate the FEA results with analytical calculation results. In the first conditions, that is both ends are fixed, the percentage deviation with the analytical result and the FEA result is 0.23%. In the second case, that is second end conditions, one end is fixed and the other end is pinned, the percentage deviation between the analytical calculation result and FEA result is 0.11%. In the third case, that is both end is pinned, the percentage deviation between the FEA result and analytical calculation result is 0.05%. In the fourth case, one end is fixed and the other end is free, the percentage deviation between analytical calculation result and the FEA result is 0.01%. So we can see that the percentage deviation is very low while comparing the analytical and FEA results. Introduction to shear center. Shear center is one of the important concepts in design engineering. Now we are looking into the definition of shear center. The shear center is defined as the point of a member at which all the resultant shear force of the member is subjected. At this point, the member is subjected to simple bending with no twisting or torsion. That is defined as, if we are applying the load to the shear center, the material undergoes only bending due to the applied load and there will be no twisting or torsion is acting on that particular structural member. Next, consider a beam with a cross section I. Here the I section is symmetric in both x-axis and y-axis. And if you are applying load through any points on x-axis or y-axis, there will be no twisting or torsion in the beam, and it is mainly due to the
symmetry of this I-beam along the x-axis and y-axis. And here the meeting point of the x-axis and y-axis can be defined as the shear center. If we are applying load any point apart from this x-axis and the y-axis, there will be twist or torsions will develop in the structure. Now we are going to discuss about the significance of shear center in design engineering. It is important to find the shear center for beams and sections that are undergoing majority of load under torsion and twisting. At this point, the member may fail only due to bending or any other force apart from torsion. Now we are going to discuss about the shear center location in different sections. In the C channel, it is symmetric about the x-axis that is represented as red line in the image, and the shear center location is outside the C channel represented as the black dot. In the square section, the location of the shear center is the meeting point of its diagonals. In the circular section, the location of the shear center is at the center of the circle. We shall discuss more details about shear center and its applicability in buckling calculations in the upcoming webinar sessions. Thank you.